mode.
Hi everyone, welcome to another IGDA Webinar Wednesdays. Today we're going to be talking about AI. It's the second week of the month, and that's what we do on the second week of the month. And we're delighted today to be joined by Kevin Dill from Lockheed Martin's Advanced Simulation Center. Kevin's had a pretty long history in the industry before going all corporate. But one of the things that he knows about more than anybody is utility theory, and he'll be telling us a lot about that and how it works and what it is. You can find more information on the website at igda.org/webinars. And as a reminder that this session will be recorded. You will be able to hear me. You won't be able to hear me. You'll be able to hear Kevin, and none of us will be able to hear you. But if you have a question, you can put it into the question box on the side, and we'll get to those at the end. So without further interruption, Kevin, take it away.
All right. So I'll start with a little bit of an apology. Wow, that's missing out. There we go. Luke asked me last April if I would give a talk, and of course I said, well, I'm completely buried. But I'd be willing to do one if you can't find anybody else. And then he found somebody else, and he said, well, how about October? Sure, October is a long way away. I have plenty of time. So by then, of course, I'm sure I can have a talk. And then October rolled around. I said, I'm completely buried. So to make a long story short, I put this talk together this morning. But I think it's going to be great. It's, as Luke said, something that I can talk about forever ad nauseum. So hopefully it'll be good. So to give a little bit of my background, I worked in the games industry for about 10 years, so you know where I'm coming from on a wide variety of projects. There's sort of strategy games over there on the left, sandboxy, Zoo Tycoon games and simulation games in the middle. I did boss AI for Iron Man, and then the last game I worked on was Red Dead Redemption, where I worked on the ambient human AI. I left the games industry about 5 years ago to work for Lockheed Martin, where I still do a lot of AI. So on the left is character AI for, this is cultural training. So we're training Marines just before they were getting deployed to Afghanistan. We have these mixed reality characters. So this grandmother you see in the back isn't a human, that's an image projected on the wall. And they can interact with her, and mostly she screams at them. We call her the angry granny. I've also been leading a project to build educational games, so STEM games to teach 9th and 10th grade math and programming concepts. That's sort of in early prototyping, and running some experiments around that too to see how successful it is and stuff like that. And I do other AI. I do AI for large naval simulations and that sort of stuff. So today I'm going to start out talking about rule-based AI, a little bit of a response to Damian Isla talk that none of you guys heard. But Damian, I went to a talk Damian gave the other day on behavior trees. And of course, Damian really likes these sort of sequence selectors. I forget what term he uses to describe them, but I call them rule-based AI. And I really like utility-based AI, and we have this fun sort of back and forth about it. So if it seems like I'm responding to something, you can imagine Damian taking the other side, except that he's not here, so he won't be. Talking about some of the challenges that you face with that sort of approach. I'll talk about utility-based AI, some of the different approaches for selection, some best practices, and then hopefully if I have time, I will get into some of the challenges in utility-based AI and how we can address them. But there's not a right answer. Neither Damian nor I are right or wrong. We just prefer different approaches. And each approach has places where it does really well and places where it struggles a little more. And either approach can be made to work regardless. So the big idea behind rule-based AI is that the AI is essentially a list of things that you could do in order. And so you go down the list, and each list has a predicate and an action. And the predicate is, under what conditions should I do this thing? And the action is, what should I do if the predicate is true? And you just go down the list in order, and the first one whose predicate returns true, that's the one you pick. This is what most behavior trees do. Damian introduced the idea of behavior trees many years ago based around what they'd done in Halo 2. Red Dead Redemption had a rule-based AI at its core. We called it Teleo Reactive, which is a fancy term that means rule-based AI. And we, in Red Dead we had hundreds and hundreds, I don't know how many, but certainly hundreds of rules, pages and pages and pages of text files of rules. So to give an idea, here's a simple rule-based AI, right? So I'm an AI soldier responding to the player. So I have this list of rules, right? If there's a grenade at my feet about to explode, then I react to the grenade. No grenades, then I take cover. If I'm already in cover, then I reload my weapon. If my weapon has bullets in it, then I fire at the enemy. And periodically, when I've fired for a couple of seconds, I have a timeout on fire, and when that timeout is keeping me from firing, then I duck back down behind cover. Right, so this is pretty good, right? Most of the time I'm going to be in cover firing at the enemy. If I run out of rounds, then the reload behavior is going to take over. It's going to pop me out of fire. It's going to have me do my reload behavior, and once I'm done reloading, then I drop back into fire naturally. If for some reason my cover is invalidated or I need to move cover, then take cover will pop me out of fire. If a grenade lands at my feet, then react to grenade will pop me out of fire. But once those things are done, I go back into fire. So this seems pretty good, right? But what happens, when you start looking at it for real? So QA gets involved, and they say, well, this is great, but right now, if you're firing and the player has directed fire hitting all around you, right, or even hitting you, you don't duck. You just keep shooting at them. So all right, fine. I'll add another instance of duck above fire, and I'll say, if there's directed fire coming at me, then I'll stay down behind cover and let somebody else pop up and fire at the player. And QA says, well, that's great. But sometimes when you react to grenade, you dive on the ground, but you dive on the ground out in the open, and then so the player can throw a grenade, and that makes you dive on the ground, and then they can easily pick you off. All right. So I'll put take cover before react to grenade. In a special case, if there's a grenade there, then I take cover, but now I try and take cover from the grenade and also from the player. And then QA says, well, that's great. Except sometimes now you're taking cover from the grenade and you're exposing yourself to you're taking cover from the player, but you're exposing yourself to the grenade. So now I have, well, if I can't find cover from the grenade, then I'll react to the grenade and let the player shoot at me because that's lower risk. And then once the grenade goes off, then I'll take cover. Then so you start to get this ordering problem, right, where react to grenade is more important than take cover, except when take cover is more important. And take cover is more important except when react to grenade is. And this is why in Red Dead we had so many rules. It wasn't just that we had that many different things the AI could do, although certainly there were a lot. But also there's a lot of this sort of repetition and this sort of almost race condition fighting. And more generally, there's this problem when your priorities are fixed that there are exceptions. So, to take it a little farther, what if I wanted to add in a first aid option, right? So my buddy has been shot, and I want to do first aid on him. Well, how important is doing first aid? Well, it really depends. How badly is he wounded? What are the threats in the area, right? It could fall lots of different places. So often priority is more dynamic than this, right? I like to say there's a lot of subtle nuance in the situation that could adjust how important it is to do different things. That's one problem. Another problem with rule-based AI is that it has a strict ordering, so there's no randomness in what you do. Given the same situation, you always do the same thing. So let's imagine a slightly different problem. Now instead of the general combat problem, we're looking just at reacting to grenades, right? So a grenade is landed at my feet. There are a couple of things I can do, right? If there's cover between me and the grenade, I can just duck behind the cover. Otherwise, I could dive for cover. I could throw the grenade back. I could kick the grenade away. I could potentially even dive on top of the grenade, right? So how do I decide what's the most important? Well, dive on top of the grenade is actually a great action, but only if there are other people there, so maybe it should go at the top. But really what I want to get at is if I throw a grenade into a bunker with 5 guys in it, they shouldn't all do the same thing, right? They shouldn't all dive on top of it. They shouldn't all kick it away. I should see variety of actions. So what I really want to do is I want to rank these according to how appropriate they are. I want to throw away the ones that are bad choices, right? So I shouldn't dive on top of the grenade if I'm the only one there. I shouldn't try and duck behind cover if I have no cover. I shouldn't throw the grenade back if it's 10 meters away and I'm not going to get to it in time. But then once I've done that, I want to be able to pick randomly. So if I've got a bunch of people, then I get a variety of responses. So what's really going on here, right? What's the matter with this sort of rule-based approach? It uses Boolean logic, right? Black and white logic. I either do something or I don't do something. There's no sort of fuzziness of, well, it's this good and something else is that good. And that's great when there's a clear best choice. It's great when the ordering is pretty consistent of how important things are. But it struggles a lot more when there are multiple choices that are reasonable, when we want variety in our responses, or when there's a lot of subtle nuance that could drive how good something is. So an alternative is utility-based AI. And in contrast, utility-based AI uses floating point logic, so it's sort of think of it as shades of gray. So in utility-based AI, you have a heuristic function that measures the relative goodness of each option, right, of each thing that you could pick. And sometimes we call that relative goodness utility, sometimes we call it priority, sometimes we call it weight or rank or force or value, or pick your favorite word. Utility, priority, and weight are probably the most common ones. And that utility should be based on the current situation in the game. So this isn't just weight-based random where I have fixed weights and I pick randomly using those weights. This is I evaluate the situation in the game and I use that to drive my decision making. Or not, right? You can still have cases where there's something with a fixed utility. And we'll come back around to that a little bit later. But it's important to realize that when it makes sense, fixed utility can be just fine. Sometimes you will just want to say the utility of this thing is 17. And that can let you get at some useful patterns in the way you apply utility. So coming back to this grenade example, right? I can say, well, the utility of duck is 0 if there's no cover in between me and the grenade. Otherwise, the utility of duck is really high. The utility of dive for cover is, sort of middling to average. It's better if there's something that I can dive behind. It's not as good if I'm just diving onto the ground. The utility of throwing the grenade back depends a little on how long the grenade's been there and how far away it is, and whether I know where it came from. The utility of kicking it away depends a little on, do I have somewhere that I can kick it? Is there something like a grenade sump I can kick it into? Or a clear line that I can kick it away that I think I can safely do that. The utility of diving on top of the grenade involves not only some things about my personality, how many other people are with me, who those people are, how I feel about them, right? Are these my close buddies who I've spent a lot of time with, or are these, am I the new guy in the unit and I just met these guys, right? Or maybe even, I'm for some reason resentful of them, then I'm much less likely to dive on top of a grenade to save them. And then I can throw all of that in the hat, right? So I set the utility to 0 for the things I don't want to do, and maybe I pick randomly, or maybe I apply some randomness to each utility. So how do we do that selection? There are two really common ways. One is just to take the best one. So I calculate the utility of each thing, and then I take the one with the highest score. And we worked on Cohan 2, for instance, was a real-time strategy game. This is how the AI in Cohan 2 was driven. So all of the things that the AI could do were scored, and then the one with the highest score won. There are some common tricks that you want to use if you're going this route. One is it often helps to add a little bit of randomness. Sometimes just the situation can be varied enough that there's enough randomness in the situation. But sometimes you want to pick a random number between, I don't know, 0 and 100 or whatever. It depends on how big your utilities are. And add that on. We call that a fuzzy factor. Another thing is, once you pick something to do, you don't want to be flip-flopping back and forth. So especially if you're using some randomness, you want to apply some hysteresis. And hysteresis just means I give a bonus to the thing that I'm currently doing. So, maybe if the utility of something is 300, then if I'm currently doing it, I add 100 and I make the utility 400. And the last thing that we wanted in Cohan, which was a useful trick, is oftentimes there was something that was important to do, but it was expensive. So upgrading your settlement, for instance, was a really important strategic decision to make. But it took a lot of money, and so you had to kind of save up resources. So you had to save money in order to be able to do it. So if you keep kept doing other things because you had enough money for them right now, and they were the highest priority valid option, then you'd never be able to save enough money to upgrade your settlement. That was a guaranteed way to lose the game. So we had this notion of goal commitment, right? We would say, if at my current rate of income, I'm going to have enough money to do this thing within some amount of time, 30 seconds or 2 minutes or whatever amount of time makes sense, then I'm going to commit to it, and I'm not allowed to do any lower priority things. So I'll just do nothing with that particular resource. I can still do other things with other resources. The other way to pick is what I call relative utility. More commonly, it's just called weight-based random. So the notion here is I calculate the weight of each option, and then I pick at random. So if I have an option with a weight of 3 and an option with a weight of 1, then 3/4 of the time I pick the 3, and 1/4 of the time I pick the 1. And the math for that isn't hard to work out. You just add them all up, and you pick a random number from 0 to the total amount, and then you walk down the list and subtract off the amount of each option until you get below 0, and that's the option you take. Again, you can, weight-based random can be done with fixed weights. If you just want to say, 3/4 of the time my characters should dive for cover, and 1/4 of the time they should dive on top of the grenade, and that's good enough for me, right? I don't want to have to think hard. I just want it, that ratio of actions looks pretty good. Then you can just use fixed weights. If you want to work in more situational logic to make it more reactive to what's really going on, then you can use dynamic weights. One common trick with weight-based random is to say, I want to pick at random, but I want to make sure that I'm picking something reasonable. And you probably hear me say this phrase multiple times, right? Random but reasonable. So I want to get a variety of reactions. I want the reactions to not be predictable, to not be something that, not be necessarily something the player can know is going to happen or expect is going to happen. But at the same time, I want to make sure that what I do makes sense, that it doesn't look stupid, because looking stupid is the absolute worst thing you can do. So I'm going to remove any options whose weight is less than, say, 10% of the best option or 1% of the best option, whatever that number is. And usually you need to set that number on a per decision basis. 10% works pretty good in most cases, but sometimes I have lots of little options whose priority needs to add together. So for example, imagine I'm choosing targets, right? And 50% of the time I want to shoot at the platoon leader. I'm a sniper, and 50% of the time I want to shoot at one of the other 14 soldiers in the platoon. So if I'm using 10% as my screening, then I give the platoon leader a score of 50, and I give the other guys a score of 50 divided by 14, whatever that is. Well, all of those guys are going to be less than 10% of 50, so I'm going to screen them off, and I'm always going to shoot the platoon leader. So you need to be able to adjust it on a decision-specific basis. But that's a really useful trick to make sure you don't end up just happening to pick some low probability option that actually looks like crap. The other trick that sometimes is useful for weight-based random is what some people call ping pong ball squared. So the idea behind weight-based random is I'm just throwing a number of ping pong balls into a hopper based on the weight of each option, and then I'm picking one ping pong ball out of the hopper, and that's the one that I pick. Ping pong ball squared is I square the weight, so I square the number of ping pong balls that I throw in for each option. What that does is it increases the separation. So if I have two options, one with a weight of 1 and one with a weight of 2, instead of being 2/3 likely to pick the one with a weight of 2, I'm 4/5 likely, right? Because I square the 1, it's still 1, I square the 2, and now it's 4. So it makes the better options be more likely to be chosen while still giving some chance to the lower priority options. It's a little bit of a hack in my mind. It's better to write your utility function so that it does that for you, but sometimes it's useful. So the first best practice that I'll mention, I've talked about 2 different ways to pick, but something that's really powerful is this notion of dual utility AI. And I didn't come up with this. This is something they were already doing on Zoo Tycoon when I joined that project, but I think it's brilliant, so I've run with it ever since. And the notion is that I use both absolute and relative utility, right? So I use absolute utility to divide my options into categories. And I tend to call that force. So if the force of something is 10, then I'm not going to consider any options whose force is less than 10. And then from within all of the options whose force is 10, I use weight-based random to pick between them. So again, here I finally put random but reasonable on a slide. Again, this lets me use the force to eliminate categories of things that don't make sense, and then use weight to ensure that I have randomness within a category. So in Zoo 2, we did things like we would set the force of dying to 1,000,000, right? If it's time for an animal to die, then the animal should die. That's it. That's the thing you should do. Don't consider doing anything else. We also, in later expansions, we added things like marine shows. So in Marine Mania, we added, you know, the marine shows like at SeaWorld where the dolphin goes and jumps through the flaming hoop and stands on its tail and does a bunch of tricks, and the audience sits in the splash zone, and it's all very exciting. I love to go to those when I was a kid. So that's a thing that we added. We want to ensure that the animals do the right thing, so the animals need to come into the show tank a little bit before the show. They need to line up in front of the trainer. When it's time, then they need to go do their trick. After they do their trick, they come back to the trainer and get a treat. And after they get their treat, then they just go back to lining up and waiting for the next trick, and it cycles through this. It's sort of an FSM basis, right? This is just to see it cycles through the sequence over and over until the show is done. So in order to do that, we just carefully set the forces of those actions so that the current one would always be the highest force. Any higher force ones would be invalid. That wouldn't be the only way to do it, but it let us work into the dual utility system that we had. Coming back to combat AI, you could have react to grenade options that are very high force, right? Because reacting to grenades is very important. You could have a reload action that's lower force. You could have a first aid action that maybe is variable force, depending on how much you like the guy and whatever other considerations go into it. Then once you've found the highest force within that category, you pick random but reasonable. So more specifically, these are the 4 steps that you use for picking an option. So the first thing you do is you eliminate any options with a weight of 0, right? Because if they've got a weight of 0, they can't be selected in weight-based random. The probability of them being selected is 0. And that's also a convenient way. You can just mark options that don't make sense right now by giving them a weight of 0. And so it's an easy way to eliminate things. It makes a convenient convention. And conventions will, again, I'll talk about this in a couple minutes. But having good conventions is very important to making all of this manageable. Once I've eliminated the weight 0 options, then I find the best category, right? The one with the highest force. Within that category, I find the highest weight, and I screen options that are less than some percentage of that weight, and maybe I square the weights if I want to. And finally, I pick at random from using weight-based random from the options that remain. So this is sort of my preferred go-to decision-making approach, especially when the decisions are complicated, when there's a lot of nuance in there. So how am I doing on time? Oh, I'm going really, really fast. So there's going to be lots of time at the end. Hopefully everybody's thinking of lots of good questions. Another best practice is this notion of modular AI, which I've been harping on for a while, and people have started picking up and running with. So modular AI can do lots of things, and I'm not going to try and get into it in detail today, but one of the, sort of where I started with it, and one of the really useful things is to have this idea of considerations. So the notion is there are lots of decisions that you're going to make in your game. And each one is going to be different. But the types of things that drive your decision making, right, the considerations that go into deciding the utility for each option, right, how good it is there are far fewer types of things to do that. So for example, you might look at the distance between 2 objects. Maybe it's the distance between me and a target. Maybe it's the distance between me and a grenade. Maybe it's the distance between a target and the exit, because I have to keep from getting to the exit. So distance could drive priority, right? Timing could drive priority. When we talked about firing your weapon, we said maybe you fire your weapon for 5 seconds. And by the way, that's a real world thing. So back before I was in the games industry, I was in the Army. And there's something called a 3 to 5 second rush. The idea is when you're attacking the enemy, one person lays down cover fire, and the other person pops up and runs forward for 3 to 5 seconds, and then they dive back down behind cover. Because it takes 3 to 5 seconds to acquire a target and shoot at them, especially when you have cover fire coming in. And then you swap, right? The guy who just did the 3 to 5 second rush now lays down covering fire. And the first guy does a roll to the side and then pops up and runs for 3 to 5 seconds. So there's a timing consideration in my head there saying, I'm going to do this for some random amount of time between 3 and 5 seconds, and preferably more towards the 3 end because I really don't want to get shot. And then I'm going to get back down. You see that in games all the time where, an enemy will pop up and shoot at you for a couple of seconds, and then they duck back down behind cover, and maybe somebody else pops up, and it sort of turns into whack-a-mole. Maybe there's a health consideration, right? How much damage have I taken? Maybe there's shots fired, right? This isn't have I fired shots, but is the player fired shots, or have I heard shots fired? And shots hit, right? Have I taken damage? Maybe I just use the health consideration for that. But these sorts of factors can drive lots and lots of decisions. So I use distance all over the place, right? I use timing all over the place. Often once I've done something, like a fidget animation, right? So the idea behind a fidget animation is I want to break up my standing idle animation. So I add in stretch animations and tie my shoe animations and rub my nose animations, whatever sorts of fidgets I add to break up that idle. But once I've played a fidget, I don't want to play it again for a while. So I can use a timing consideration to ensure that it doesn't play again for some amount of time. Another consideration is just a plain fixed value consideration that just says, the weight of this is something, or the force of this is something. So now I've got all these different considerations, and as I'm putting together the AI, right, I'm enumerating all of the options that could be selected by this AI reasoner, and then for each option I'm saying these are the considerations that are going to be used to determine how good that option is. I'm going to use a fixed value consideration to give it a default value. I'm going to use a timing consideration to adjust it, to set its weight to 0 if I shouldn't do it right now because I just did it recently. I'm going to use a health consideration because as my health increases, the importance of this decreases because this is a use medpack action maybe. Each consideration, so there are lots of ways that you can combine considerations together, but a good sort of starting point, what I use 95+% of the time, is to have the considerations have 3 different parameters. The first is the force, the second is a base weight, and the third is a multiplier. And the way that I figure out my 2 utilities, the absolute utility is just the max of the forces. So when a consideration says that the force should be 10, it's basically proposing that. It's saying, I know the force needs to be at least 10, but there might be some other consideration that knows this is even more important than that. That'll say the force is 17. If so, listen to him. But if he doesn't speak up, then listen to me. And then we calculate the weight by first adding together all of the base weights and then multiplying that sum by all of the multipliers. One of the nice things here is that any consideration can set a multiplier of 0, and because multiplication is commutative, that will set the total weight to 0, and when the total weight is 0, the option gets screened out. So any consideration can say, you know what, I'm vetoing this. Right now, don't do this. This isn't a good option given the situation. So the distance consideration can say, you know what, he's too far away. Don't try and throw a hand grenade at him. You can't throw that far. The timing consideration can say, I just threw a hand grenade a second and a half ago, and the game is too hard if I use too many hand grenades, so I'm not allowed to throw another hand grenade until 20 seconds have passed, so I'm vetoing this option. The shots fired consideration can say, I'm not allowed to shoot back until the player shoots at me first. because I don't aggro on distance, I aggro in response, whatever. So I'm detailing this option. They also can adjust the multipliers can also obviously be used to, and base weights can be used to scale. Typically what I do is I have a fixed value that sets the base weight, and then I tweak from there with multipliers, but your mileage may vary. If you allow negative base weights, you have to be a little careful that you don't just screen options with a weight of 0, you screen options with a negative weight as well, but again, there's no magic there. So this solves everything, right? It really doesn't, and probably just listening to that last explanation, you're thinking, well, that sounds really hard and complicated to balance. And that is the challenge with utility-based AI, and that's why Damian went away from utility-based AI and more towards Boolean AI. Because you've sort of got the ordering problem. So we all remember the ordering problem from rule-based AI. You've got that problem on steroids, right? Because now I can't just look at these things and say, this is the fixed order that they go in, and yeah, react to grenade appears twice because the conditions are different. But that's not that hard to understand. And as you get a lot of them, yeah, it gets sort of painful. But now imagine that instead of that, there's a value function that's calculating that ordering dynamically. That can be a little painful. And you also can get too much randomness. So you get, well, it seemed reasonable to have the throw the grenade back option, but, in this situation it wasn't really reasonable, but it got randomly picked. And so I should have screened it out, as opposed to, well, now I screened out too much, and now I never throw the grenade back anymore. But the animators spent hours making this beautiful grenade throwing animation just so I could do that. So the utility-based AI is sort of the converse of rule-based AI, right? It's great when there are a bunch of different choices, any of which is reasonable. So no matter which option I pick, the player is going to look at it and be able to tell themselves a story that explains why I picked that thing, that makes that decision make sense, that makes it feel good. And really, I don't have to put too much thinking in. If the player can tell themselves a story about why something is reasonable, I don't need to overthink it. I can just do that thing and let the player tell themselves the story, and they'll imagine a level of intelligence that I'm just flipping coins here. Utility-based AI is great when I want variety in my responses. I don't want to do the one good thing. I have a bunch of good things, and I want to make sure that everybody doesn't do the same thing. I don't want it to be predictable, or I don't want a room full of people all doing exactly the same thing. And utility-based AI is great when there's a lot of subtle nuance, right? When I really want the AI to be able to react to the situation in-game based on the details of that situation. But it struggles when it's important to do really good things, right? When there's this sort of strict fixed ordering, and it's important that I don't try and fire because I need to reload right now, right? My weapon is empty. And so I shouldn't be randomly picking fire. I need to just know, nope, now is the moment to reload. So how do you make sense of that? And some of it just comes from doing it. You have to, at least for me, when I first started using utility-based AI, I mean, I'd done bits and pieces of it, but when I went to work at Timegate Studios to work on Kohan 2, which is a real-time strategy game, and Axis and Allies, which were we created both of these games on the same engine at the same time. They're both RTSs. It was sort of mandated to me, you're going to use this, we called it a goal-based AI, but it's really a utility-based AI system that's similar to what we did in the previous Kohan. It's going to look basically like this. And so I had to wrap my head around it, and, and everything is a goal, and everything gets considered together. And there were a bunch of these sort of mandates that were handed to me that it took me a while of beating my head on until I sort of started to see, okay, well, here's the trick I can do to make it do the thing I want in this situation. And so you build up conventions. So you build up over time sort of skill at thinking in terms of floating point numbers, and expressing things in terms of floating point numbers and balancing those numbers. With that said, there's more to it than just do it until you're good at it. So one is to have a set of conventions that work really well. So if you've got, especially if you've got more than one person on the team writing AI, but even if you're the only person, it really helps to have a set of conventions. So in Kohan, priorities between 0 and 100 sort of meant a certain level of importance, and between 100 and 1,000 meant a different level of importance, and 1,000 and above meant a different level of importance. Another thing that helps is, often you have things that can run in things that use different resources, so they aren't really being considered against each other, right? So the priority of building a sawmill doesn't need to be balanced against the priority of attacking an enemy city, because the sawmill uses gold and attacking the enemy city uses military units. Another solution is patterns. I gave a talk on this at GDC a few years back. But just as patterns have helped us in programming generally, and we have things like the factory pattern, we can have patterns for utility, ways we can use utility. So a very simple pattern is that convention that I said where a multiplier of 0 is a veto. So, here's a pattern that I can reuse, right? Anytime I want to veto anything, I just set its multiplier to 0. And anytime I see a multiplier of 0, I know that means that I'm vetoing. Another pattern, so I can do rule-based AI using utility by just using fixed forces. And just, as I did in Zoo 2 on the animal shows, the most important thing has the highest force, and the next most important thing has the next highest force, and the next most important thing has the next highest force. And the weight is my predicate. So if the weight returns a non-zero weight, then this is a valid option, and I do it. If the weight returns a 0 weight, then it's not a valid option. I drop down to the next one. So one of the reasons I like utility-based AI is I can do simple things like set up a rule-based AI inside of it. Of course, it's a little bit awkward to do that. But if I'm only going to have one type of reasoner, utility-based AI can do simple stuff. I can do that. I can do sequences where I do this and then this and then this and then this with utility and timing considerations, for instance, where the timing consideration just says if I've ever done it, then don't do it again. But I can also do these sort of subtle, nuanced, lots of weights go into calculating how good each thing is, and then pick one at random decisions. But the last solution, and really in my mind the best solution, is to have modular reasoners. So I talked about considerations and the way I can make considerations modular, define it, so I didn't go into too much detail, but once you've got this set of considerations, right, you can create a factory that can load a chunk of XML, look at the type flag on it and say, okay, this is a distance consideration or this is a timing consideration, instantiate an object of the appropriate type, and pass the chunk of XML into it so that it can configure itself with, what are the two objects that I'm measuring distance between, and then how do I use that distance to set my values. We can also have modular reasoners, so we don't have to have one type of decision-making algorithm in our game. And behavior trees are great for this. So in my mind, what a behavior tree is really is not just a synonym for hierarchical utility-based AI or hierarchical rule-based AI. What a behavior tree really is a hierarchical AI where at each point in the hierarchy, I can plug in a different type of reasoner. So I could have a high-level reasoner that's doing my combat reasoning that's rule-based. It's saying, the most important thing is to react to grenades. The next most important thing is to get into cover. The next most important thing is to reload, right? So that rule-based AI works pretty good. It's pretty simple. It's pretty focused. It makes this decision for me nicely. So let's just use a rule-based AI there, right? And then I don't have to muck around with conventions for what the forces mean and trying to remember when I add a new thing where I put that in the force and not getting them mixed up. And then as I jump from one to another, having those conventions map up enough that I don't get horribly confused. I could just have a rule-based AI that just lists them. I look at the list in order. It's nice and easy to read. And then when I get to a decision where I really want to be nuanced and I really want variety and randomness, like now I've decided I'm going to react to a grenade, the reasoner for choosing how to react to that grenade could be weight-based, or it could be utility-based. And I can have another type of reasoner that does a bunch of things in order, and maybe it loops, or maybe it just does each one once, or maybe each time it's selected, it does one thing off the list, and the next time it does the next thing, and the next time it does the next thing. Those three different types of reasoners, sort of a scripted reasoner, a rule-based reasoner, and a utility-based reasoner, between them encompass most of the ways that we make decisions in games. Or if not, then add another type of reasoner. So you could add a planner reasoner, for instance, if you wanted to. If you felt like planning, you wanted to be able to reason about sequence of actions that would solve some problem, that would get to some goal. As soon as you need that, you implement a planner reasoner, and then you've got that planner reasoner, and anytime you need it, you use it. But when a utility-based reasoner, it's less about finding a sequence of actions and more about subtle nuance of the situation, then you use a sequence reasoner, or it's more about doing the best thing, then you use a rule-based reasoner. So that's all I got. If I was supposed to be 45 minutes, then I came in perfectly, or 3 minutes under. Questions? Comments, complaints, suggestions, reactions?
Shock and awe, I think.
I don't think I can, or something. I can't see the question box, so I'm relying on Luke.
No, I've got it here. Don't worry about it. There are questions coming through, one of which you've already answered, so that's good. So Rob has asked, how would you implement reasoners that evolve with the player reaction to the situations within the gameplay?
Reasoners that evolve with the player. So that sounds like I want to do some sort of learning? Is that what you're getting at?
I guess. I think, I guess it's a question about kind of learning from how the player's reacting in certain situations.
So, well, this gets back to the very first debate you and I ever had, Luke. So I tend to shy away from machine learning because I don't trust it. But, that's my bias. Taking a step back, right, in my mind, what a reasoner is a thing that has a set of options that it can pick between, and its job is to pick between them. I could write a machine learning reasoner that uses whatever machine learning technique, neural net or reinforcement learning or whatever, to learn over time which of the things works best given the situation, and then picks that one. And that's sort of a utility-based thing to do, right? So, but now I'm letting the machine learn what my utilities are instead of defining them by hand. Probably the closest that I've done to that sort of thing in Cohan 2, we wanted to make sure that the AI, for example, didn't attack over and over and over with the same piddly force if you'd been defeating it each time, and just sort of throw its units away. So anytime that a battle ended, we looked at the size of the forces involved, and we said, is this result surprising to us? In other words, did the player have a very weak force and defeat a stronger force? If so, that's surprising to us. So now, from now on, we always consider that player to be, his forces to be a little bit stronger than they actually are. We increase the combat value of his units. And the other way around too, right? So did we easily defeat the player, then now we consider his combat value as a little bit less. So that let us sort of adjust. At least, you attack the player and you lose. The next time you attack, you'll send more forces. And you lose again, then the next time you send more forces. And there's two things there, right? One, that responds a little bit to the goodness of the player, and the other is that makes it a little bit adaptive. So if we didn't balance the game perfectly, that's okay. The game will sort of self-balance. So the first attack might feel more like a skirmish, right? And they lose. But that's not actually a bad thing from a sort of an excitation curve, right? The first attack should be weak. And then the next attack will be stronger. until we finally start to win, or we run out of units.
So Rob's clarified his question a little bit, and I think it's going in a slightly different direction that's probably worth exploring. So he says that he was referring more to the player actions being the input to the learning rather than the machine learning. So I guess what we're talking about here is kind of actually learning by supervision of what players are actually doing and building the utility system from that.
So that's a really interesting area. I mean, I could give my machine learning rant. So my fear with machine learning is...
Oh, rant away, Kevin. Pretend I'm not here.
In 5 minutes or less, right? My fear with machine learning is this. Games are about creating an experience for the player. And that experience is something that a human defines, a designer defines. So my first problem with machine learning is typically what machine learning does is it has, again, a heuristic function that evaluates how good an outcome is and then tries to, tries different things and learns which things work to increase that heuristic. And it's pretty easy to write a heuristic for I won the game. But the goal of the AI isn't to win the game, right? The goal of the AI is to create this experience, make the game fun, make the game exciting, make the player angry. So I went to a game design talk on Monday where the speaker made the case that God of War, the whole point behind God of War is to make you angry. And everything about the game is designed to make you angry. This button mashing to open a door is really sort of intense, angry thing to do. Because the character is really angry, and that's the experience the designer wanted to go for. So how do I write a heuristic function for fun or angry? So that's one problem, right? But let's posit that you can solve that problem, that you understand heuristically what you want to do. The other problem with machine learning is that I have to trust it to do the right thing. I can't really train the machine learning until I've got the game written. So I can't, if I'm writing the game, then I can start writing the game at the beginning of the project because I know what direction we're going and I can start to build that out. But I can't do machine learning until I've got a game to learn on. Oftentimes the game changes at the last minute, and now I need to rerun the machine learning, and I'm really relying on the machine learning to work, right? It's got to produce an AI that's good or my project fails. But it's way too late in the project for me to say, you know what, machine learning didn't really work. All right, well, let's hand code something. So like I say, I am always a little bit afraid of machine learning, but I'm also not at all expert in machine learning. So if you want how to do machine learning stuff, you're probably asking the wrong person. Paul Tozer's done some interesting stuff about, he gave a talk at AID a number of years back now about representing World of Warcraft player behavior in terms of a behavior tree, for instance. So whether you do machine learning or not, I think thinking about what the player does in terms of how you would write an AI for it is, at the very least, a very interesting exercise. And he also argued that you could use it to think about, as a design tool, to think about how to change the design over the time, change the AI for the player, sort of changes the gameplay, changes the design.
I guess that's kind of the direction he was headed in with City Conquest, which would have been after the AID talk, I guess.
I think Paul's, I don't know if Paul's continued to talk and write about that. I think he's chased that idea some more. So that might be somebody to Google.
Yeah, I think there's like a 6-page Gamma Sutra article. Sorry, a six article series all about that stuff. That's definitely out there. So we've got another question from Dan, who asks, does utility-based AI negate the need for interrupts? So I guess the question there is kind of, can you rely on your utility system to do the right thing, or do you actually have to kind of say, oh, what's happening here is not right, and let's have a rethink?
So, I mean, it certainly doesn't negate the need to, the situation changes, and so you need to do something different, right? A grenade just landed at your feet. Now you need to react to it. So that interrupts whatever behavior you were having before. there's a notion that, that we first saw back in finite state machine days, of a state stack where, I'm patrolling, I'm moving through the woods, I'm path planning to where I'm going to do an attack, and I get ambushed, right? So I pop or I push a react to ambush behavior on top of the state stack. And I react to the ambush, fight through the ambush, run away from the ambush, however I choose to react. Once the ambush is done, then I pop that back off, and now I drop right back into my patrol behavior. Sort of the same notion as subsumption. And that's, to me, one of these really useful tricks that you can apply to any kind of AI. So, being able to say, I'm reacting to a grenade, so now I'm going to push this different utility-based AI on top, which is react to grenade stuff, and then I'm going to pop it off once the grenade explodes, if I'm still alive. I'm not sure if that's quite what he meant by interrupts, though. So is there?
I don't know. If Dan would like to clarify that, then that would be great. And we have no other questions, so unless somebody has something in the next 20 seconds or so, or Dan comes back with a kind of, no, doesn't look like we're going anywhere here. Okay, so all that remains to do, oh, here we go, no, Dan's here. Interrupts, as mentioned, involve software publicly available AI code. They were just something inserted into the AI cycle that stopped the current action. So yeah, I mean, that's kind of where we were talking around, I guess.
Yeah, game AI to me is sort of it's always a mishmash of useful concepts, right? And that idea of interrupts, or I sort of think of it as behavior stacks, is a really useful one. A more academic person might call it subsumption, or maybe I'm misusing that word, I'm not sure. Hierarchy is another great one, right? So we had hierarchical planners and hierarchical finite state machines, and early behavior trees in some ways could be characterized mostly as hierarchical rule-based AI, at least in my nomenclature. But the notion of just, what I think behavior trees really are is just hierarchical reasoners. And the nice thing about that is tuning the AI, no matter which approach you take, right? Tuning the AI is always the hard part. But hierarchy lets me break the number of things I'm thinking about at once down into smaller pieces. And since, the difficulty of tuning is exponential or worse than linear in any case on the number of options that I'm considering, that improves the ease of tuning, which is an important factor in getting a good result. But lots of, any trick that you can find to give you a way to say, in this situation, do this, in a generic, repeatable, comprehensible way is a useful thing.
Yep. I mean, fundamentally, as a researcher, I rail against that kind of thinking because we should be moving towards general AI, but realistically, yeah, you're right.
When you guys solve general AI, then I will be sure to put it in my games. But in the meantime, okay. I'm not going to hold my breath.
There we go. You heard it here first. As soon as we solve the big hairy problems, Kevin will shove it in. So there is commercial viability for us now.
Absolutely. You can also take over the world that way.
Cool. Well, thanks for making the time to come and talk with everybody, Kevin. There's no final questions coming through. So I see you've got your email address up here. You are on Twitter, as I recall, but not often or at all.
No, I really don't. I'm really not on Twitter. I'm sort of on Facebook.
Okay. So yeah, so thank you for coming and making the time. So next week we're going to be doing Game design, it's the third Wednesday of the month, and that's going to be Unity's Oscar Clarke talking about something to do with the things that Oscar Clarke knows about. So thanks a lot for coming out, everybody. I hope that's been useful for you, and again, thanks to Kevin for making the time. And we'll see you next week.